Hi guys, John the Quant here. Today's question is interesting because it's quantitative, but it's not strictly mathematical. In fact, to answer this, you need to think about it from three different perspectives. You'll need to understand probabilistic modeling, then you'll need to understand probabilistic approximation, particularly using the central limit theorem, and then third, you also need to understand how probability works in the real world. And that sounds like a lot, but this is the kind of thinking you need to be able to do to be successful in any quantitative career. The question goes like this. A rideshare company wants to increase the frequency with which its existing customers purchase rides. And to do this, they want to give some portion of their customers a $5 gift card. And they want to do it in such a way that each customer has the same probability of receiving a $5 gift card. So, how much should they budget for this promotion? Now, hopefully, you hear that question and you're already thinking and you say, well, how many customers does the company have? And the hiring manager says, I don't know. And then you say, well, what's the probability that a customer gets picked? And you say, I don't know. Well, with such a lack of information, what can we possibly figure out? Let's head over to the iPad and see. Right, here's our problem, okay? Your company wants to give a portion of its existing customers $5 gift cards, with each customer having the same probability of receiving a gift card. How much should they budget for this promotion? Well, first, we got to realize that we're given $5. We need $5 times the number of people that received gift cards. I misspelled receive. Yeah. So this is really what we're looking for. Now here are a few hints. Each customer has the same probability of receiving a gift card, which means that people are independent. Let's say customers. Customers are independent. And they all have the same probability, but we don't know what that probability is. So we're going to call it P. P is our probability of getting a gift card. And we don't know how many customers there are. So we'll say there are N customers. Now, hopefully, you guys are recognizing that this is, because they're independent, what we're really doing is N independent draws from a Bernoulli distribution with probability, there we go, equal to P. And hopefully you guys are recognizing that N independent draws from a Bernoulli distribution with probability P is actually a binomial distribution. So here we have N choose X, that's the number of customers that receive gift cards, that's what X is, times P to the X and 1 minus P to the N minus X. That's a binomial distribution. And hopefully, you'll remember that the expected value of X is N times P. Now, you could easily just write that or say that, but you would be wrong. You'd only be getting it partially correct, okay? The expected value of X is not going to account for all possible scenarios. Because this is the real world, you only get to do this once. So the probability that X is actually greater than NP is going to be close to 0.5. So that's why this answer is a fail. What you need to realize here is that as N gets large, the binomial distribution actually approaches converges in probability, say, to a normal distribution. So for large N, a binomial distribution with N and P is approximately equal to a normal distribution with mean NP and standard deviation equal to the square root of N times P times 1 minus P. You might see this sometimes written as the square root of N times P times Q. Q is just equal to 1 minus P. So with this in mind, think about a normal distribution centered at NP. Now, if you had said this one up here, this incorrect thing, then you would actually have only shaded in, only covered this half of the distribution. And that's no good because that gives you a 50% chance of blowing your budget. Nobody wants that. So what we really need is to pick some number up here. Say that covers 95%. So this is the 95th percentile of this normal distribution. And the 95th percentile is approximately equal to the expected value of x plus 2 times the standard deviation of x. So this number here is actually NP plus 2 square root of NP 1 minus P. And that's going to cover everything to the left of that line. So only 5% of the time are you going to blow your budget. And that's why this is the correct answer. Now let's head over to the computer and we'll see why we're going to do a simulation to show that this does hold up. All right, here we're just doing this in Anaconda prompt. I'm really working without a net. So to prove that this works, we're going to need NumPy, because NumPy will allow us to get random variables, random draws, and we're going to need Seaborn to make some nice histograms. The first thing we want to do, let's say N, okay, is 1,000. They have 1,000 customers. That's a small number, but it'll be big enough for us. And let's say they want to give about 20% of their customers $5 gift cards. So now we need a, let's say random binomial sample. Now random binomial sample, use np.random.binomial. We'll say n is n, p is p, and the size we want, 1,000 of those. So this is going to perform this experiment 1,000 times. And we want to show that the normal distribution is approximated by that sample. So we're going to draw from np.random.normal, and this time we'll have the loc be n times p, okay, the same mean, and we'll have the scale be the variance or the standard deviation, which is the square root, np.square root of n times p times 1 minus p. And we'll have it do that 1,000 times also. There. Now let's see what these look like. I'm going to import matplotlib.pyplot, and then I'm going to do fig, and x is plot.subplots, and this is going to let me do everything nice in Seaborn. Then sns.histplot, we're going to get a histogram here of the random binomial sample. We want the kernel density estimation thing, and we want it to be on this axis. And then we want the same thing, histplot, with the random normal sample. KDE is true, and x is x here. And let's have a look at that. Bam, you can see that the binomial one in blue behind is pretty similar to the normal sample, which is in orange. Very similar. But let's see if their 95th percentiles are approximately the same. I'm using np.quantile, and we're doing this from the random binomial sample.
And we want the 95th percentile, or 0.95, and that is 221. Now let's do the same thing, but with the normal sample. So I'm changing this to normal, and I got 220.36. Almost exactly the same, just like we thought they would be. But maybe you're thinking, hey, this is because p is 0.2. Does this work with extreme values of p? Let's find out. I'll have it be 0.01, okay, 1%. That's a pretty extreme value for p. And we're going to do the same things again. Random binomial sample, and p.random.binomial, n equals n, and p equals the new p, which is 0.01, and our size, we'll do it 1,000 times again. Then we want the same thing but normal. Random normal sample will be np.random.normal, with the location equal to the mean, which is n times p, and the scale being equal to the square root of n times p times 1 minus p. And we want 1,000 of those as well. Now keep in mind, 1,000 is still kind of a small sample for this kind of test. And we want fig and x again here. And then we'll make our histograms, the binomial one first, and the normal. There we go. 1 second. Let's have a look at that. And even with p equals 0.01, you can see that they're basically the same. The binomial sample and the normal sample are approximately equal. Now let's just check those quantiles and make sure the quantiles are the same. So we're getting the 95th percentile of the random binomial sample, and it says it's 15, and the 95th percentile of the normal sample, which is 14.94, even closer. So you can see that n matters, p does not. If the company has a large number of customers, then our approximation holds.
There you have it. This was a problem that required understanding the real world applications of quantitative thinking, and I am so proud of you for getting through it. Now hopefully you learned something, and if you did, please let me know in the comments and give me a like. And if you want to keep learning from me, go ahead and subscribe. See you next time.